Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. I have Natalie Hudson-Smith. She's the Postdoctoral Researcher at Stony Brook University out on Long Island in New York. And we're going to talk about how we can photograph the nano-sized world, which is really, really cool. So looking forward to talking to her. Welcome, Natalie. Thank you.
Thanks. I have one update. I am, as of really just last month, assistant professor at St. Peter's University now. So I'm no longer on Long Island. I'm in New Jersey.
Okay, we're close.
Not a huge move at all.
Well, tell me about your current work. What kind of research questions are you trying to answer?
So as I start up my lab as a new assistant professor, what I'm really interested in is carrying along what I learned in graduate school and my postdoctoral work at Stony Brook and Long Island, and sort of looking at the interface of what I can do in those two things. So to explain that a little bit better, my graduate studies were at the University of Minnesota, primarily interested in battery nanotechnology, so nanoparticles that are used in batteries, and what their impacts on the environment might be if they were improperly disposed of in different areas of waste disposal, et cetera, right? So things get thrown in the trash that shouldn't be, or disposed of improperly. What does that mean for these battery materials? And then my postdoctoral work was on investigating the behavior of Pseudomonas aeruginosa, which is a bacteria, and its nitrogen oxide sensing proteins. So now what I'm interested in is how, again, these bacteria interact with nanoparticles that are used for agricultural applications, and what that impact might be for the soil health, the soil microbiome, or how those bacteria might change because of these interactions that they have with nanoparticles. I feel like that's a lot to digest at once, but really the interface of materials and biology, there's a lot of chemistry in there, which is what I really enjoy.
What does that mean? What nanoparticles? What are common ones that various creatures would encounter out in the world?
Right. So if we're creatures, we're encountering them already. So I mentioned that some are used in batteries. I used to, when I was in front of students, be able to do a cool little demo where you can take out the battery from your phone and show them that it's labeled for specific types of recycling because of the particles and the type particles it contains. Most phone battery cases are now sealed shut, but they are also now used in agriculture agriculture. There are a lot of benefits to applying, say, copper nanoparticles to plants. They can help stop disease, right? And they can really help stop devastating diseases. And we also see them being used as antibacterial agents, different type of nanoparticles, usually silver, being used as antibacterial coatings or additives. Sometimes you'll see them in like anti-stink socks, right? Socks impregnated with silver nanoparticles to prevent bacteria from making you have smelly socks, that kind of thing. So we're coming across them. And then the second part of that is either they will be unintentionally released into the environment because we throw things away at a pretty high rate. We go through products quickly, and those end up in landfills, the environment, they get released. And then there's the question of agriculture. What happens when we're intentionally applying nanoparticles to a crop field, a garden, etc., because we want the benefits of them? So I would say my
I mean, they're so light, though, because they're so small. I mean, if you apply them outside, I would think they would just fly all over the place and turn into like dust clouds or, go everywhere. How could you control them at all? How could anything like that small be controlled? Or are they entrained in a liquid substance or what?
So they're usually put in a liquid dispersion, right? A colloidal dispersion, and then they're sprayed on. There's also, looking ahead, people are putting them directly in the soil. So that is another option, or giving them to the plants in some sort of concentrated way, right? Like you could decide if you're going to transplant a plant, we apply it directly to the root system and then we transplant. So there are a lot of different ways, but what you bring up is important, right? Incidental or unintended movement of these. And I think that's been a question almost always in fertilizer and agricultural products. How do you know that what you're buying will still be okay as if it gets blown away or washed away by wind, rain, storm, etc.?
Okay. So what kind of interactions are you studying in particular? The nanoparticles or what?
So I want to study, the students in my lab, dissolution and production of reactive oxygen species are where I would start, right? So they're very small and they are not necessarily soluble as we think of things being completely soluble, right? Put salt in water, it completely dissolves out. These don't necessarily do that. They're going to make colloidal dispersions and very slowly dissolve. That can be considered a benefit because you have a slow way to give a plant a nutrient. I was thinking about this the other day. I put eggshells in my compost, but I grind them up real small, and calcium carbonate in eggshells is not very soluble, so it very slowly releases calcium into the soil. So that's kind of the same idea with nanoparticles. So I want to look at their dissolution and what sort of ions they release in the soil. So for the nanoparticles I'm interested in, that would be copper ions and iron ions, and what that dissolution does to the soil environment, and if they dissolve as expected, if the soil is basic or acidic or a number of other different things that we might consider.
How would you even see them if they're so small? How would you track where they go?
So we can see them with a tool called scanning electron microscope, or you could use a transmission electron microscope. Mostly we do that before we would apply them to the soil. It's hard to put them in the soil and then come back out, right? So the easier thing to do, at least in the lab, is to have your nanoparticles, either you make them or you purchase them, and then you get a good understanding of what they're like before anything else. So we take images of them with a electron microscope, we understand how they dissolve in lab water, and then I'm thinking we start introducing them to more complex systems like soil. And it would be difficult because now you have an exact needle in a haystack problem to find them once you've released them. And that's a huge issue, but you can also look at changes in the bacteria that live in that soil, changes in the organisms that live in that soil, and see if they're behaving differently with regular soil versus soil that you've dosed with a nanoparticle that you understand very well already.
All right. I mean, I don't know, the field of, well, the nanoparticles are absolutely tiny, but I guess spread them as evenly as you could, or you dispersed, quadrillions of them over a small area, even if it's like a 1 centimeter circle. Even sampling in the right places, like how would you do that? It just sounds like you're trying to observe something that's 9 orders of magnitude smaller than let's say what's around it. That's visible or even discoverable? Like, how do you do that?
So the real answer is that finding them once they're already in the environment is very, very hard. It is much better to, in my mind, do these preliminary experiments before you release them so you know if they have negative effects, because you may not be able to find the particles that you mixed into that soil, but you can observe negative or beneficial effects from releasing them into that system.
What would be an example of a beneficial effect, let's say, that's been observed?
So one is a study that I was lucky enough to be a part of. It was led by Jaya Borgata, and it was a study of copper-based nanomaterials, so both copper oxide and copper phosphates. I said earlier I was interested in the copper. And what we did was we had set up this watermelon experiment in collaboration with the Connecticut Agricultural Experiment Station. And that meant a lot of work in both a greenhouse and a field for a lot of different scientists. None of this gets done by one person. But we had watermelon that was infected with a disease called fusarium wilt that can absolutely devastate a crop. And what we found was that these copper-based nanoparticles would suppress that fungal disease. So you get healthier plants, you get more yield in fruit at the end of the season. So that would be a beneficial effect, right? A negative effect might be something like seeing a decrease in beneficial bacterial population in a soil or something like that. So you can observe both of these once you've released your nanoparticles into your study.
So do you have any indications on what, copper or other metal-based nanoparticles are going to do? Will they be beneficial, detrimental? What's the goal here, the thought?
So that's the big question. There is a lot of evidence, so this study, other studies, that there are benefits in these type of nanoparticles for stopping fungal diseases, helping plants turn on essentially their immune system, their defense system, and increasing our yields. But I also have questions about what over-application would mean for long-term soil health. You want to keep your soil and your crop fields healthy. I have questions for what that would mean for bacterial populations. So it's really trying to balance both thinking about these benefits, which are important. We have to grow food for people. We have to have crops that can withstand blights and diseases, but we also have to have a stewardship of the land that we're planting on. So for me, it's about balancing those two things and keeping them both in mind when you're exploring the chemistry of these within the soil.
Yeah, what are some examples of the chemistry of some of these ions in the soil? What are they doing? What are the beneficial effects?
So the one thing that comes to mind and most commonly you'll see cited in the nanoparticle literature is this slow, steady dissolution. I think it's a little bit easy to understand. If you came along and you gave your garden one big fertilizer sweep all at once, those nutrients might get used up. They're all available at the same time. They all get washed away at the same time, right? So you have to keep reapplying that furniture. Because they dissolve so slowly and so steadily over time, the nanoparticles provide a way to deliver that fertilizer or that nutrient and allow you to not have to reapply. This is very similar to me putting eggshells in my compost, right? I want the compost to stay not too acidic. I have a worm farm growing in there. I want them to have calcium, but I don't want to have to give them calcium all the time. But if I put eggshells in there once, they're going to slowly dissolve and release that. So it's a little bit of a similar concept. So we're looking at slow dissolution chemistry, release of these nutrients or ions that might signal plant defense systems, and we're hoping that we get all of the benefits while we still try to be aware of what any of the risks or detriments might be.
Okay. So this is primarily in soil, but what about like aerosolized, nanoparticles? I would think, that might be like literally completely impossible to study that. They'd have to adhere to various things.
It's a good question, but maybe you should do a whole nano series. I am primarily concerned about soil. That kind of one of my pet interests, but there absolutely are people who are interested in atmospheric release of nanoparticles. And the other thing that I think sometimes people don't know, because nanoparticles is it's such a sci-fi feeling word. There are natural nanoparticles out there that humans have nothing to do with, right? So if a volcano erupts, nanoparticles are released into the atmosphere, and there's nanoparticulate in the atmosphere from that. So there are definitely people that study that, and what these particles do in the atmosphere, how long they stay there, how they move in wind and air currents, etc. But it is outside of my realm. I'm down there digging in the dirt.
In general, in the air we breathe, are there nanoparticles? I guess they would be. And what would they be? If so?
That is not something I am super up to date on. But what I do know, having been on Long Island and through New York and New Jersey this last summer with the wildfires, is that particulate matter in the size is a real measure of air quality level. So you can even look up what the particulate matter is, and it's sorted by size. They have it as PM 2.5 and PM 10 are measures of air quality, and PM 2.5 is anything that's 2 microns or less in diameter. And to give you a sense of how big that is compared to nano, there are 1,000 nanometers in 1 micron. So in the PM 2.5 air quality measurement, that could include nanoparticles, so things that are about 100 nanometers, and it can include particles that are on the micrometer scale.
All right. Well, very good. What's the best way for people to find out more about your research? Like, where can they go?
So there's a couple ways. It's just my first year at St. Peter's, but I can be looked up there. I can be contacted there. There is also, if people want a sort of more relaxed reading experience, I have a few posts at the Sustainable Nano blog. It is sustainable-nano.com, and those posts are searchable by my last name, Hudson-Smith, or just Natalie. I have a couple different posts. They range from my takes on certain things in science to exploring the chemistry of Pokemon, right? So relax to real nanochemistry stuff. And then of course, there are publications that maybe the general public does want to read or doesn't want to read, but they should know that they're out there, right? You can look up any scientist on their Google Scholar and see what they've been writing about. So those would probably be the best ways, but maybe the most fun way would be through Sustainable Nano, their blog.
Okay, well, very good. Natalie, thank you so much for coming on the podcast. I really appreciate your being here. Thank you.
All right, thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.